Okay, here's another example of a question you might encounter on number 10, where you've got a sine and cosine trigonometric equations, right? And so here we have, this is the equation to solve 6 times sine squared x equals 15 sine x minus 9. And I didn't include in the instructions, but we're just supposed to give them solutions from 0 to 2 pi, so on the main circle, right? Um, so the first thing to notice about this one is that the equation is really quadratic in form, right? It's got that kind of, if you replace sine x with just x, right? And so this was 6x squared equals 15x minus 9. You would just think of it as a straight quadratic equation, and you would put it in standard form by getting a 0 on one side, right? We just move these two things over to the other side with the 6x squared, or 6 sine squared x. And the first thing I do is just factor a 3 out, take a GCF out. All the 6, 15, and 9 all have a factor of 3. Then I go about trying to factor this stuff inside parentheses. And again, just as if this was 2x squared minus 5x plus 3, I can use the AC method, right, to get two numbers that multiply to be 6 and add to be negative 5, which are negative 2 and negative 3. So I'm just splitting up this middle term into these two terms right here, and I group them together. I factor out a common factor. So if I pull out 2 sine x out of both of these terms, this is what's left, just sine x minus 1. And if I pull a negative 3 out of these two terms, this is what I have left, just sine x minus 1, right, which then gets factored out. And we have these three factors here. 3 times 2 sine x minus 3 times sine x minus 1. If you're confused about how to do that, see if you can just replace sine x squared with just x squared and sine x with just x, and see, up here, if you can do it up here and replace this with just x squared and this with x, and see if you can factor that, because it's essentially the same thing, only instead of having an x, we have a sine x. That's why we call it quadratic in form. Okay, once we have that, we're really good to go, because we can set each factor equal to 0. Now 3 can never be equal to 0, so we don't set it equal to 0, but this factor, depending on the x we have, might be able to be 0, and same thing here. So we set 2 times sine x minus 3 is equal to 0, and then sine x minus 1 is equal to 0. And then we just solve for sine x. So sine x is equal to 3 over 2, right after I add 3 and then divide by 2. And over here, I just add 1 to both sides to get sine x is equal to 1. So we have two potential solutions. But if you think about it for a second, this one's not a solution, because there's no angle for which sine is equal to 1/2, right? The max value, if you look at the graph of sine x, is just 1. So there's no way it's going to get up to 1.5 unless it's been shifted vertically, right? Or the amplitude's been increased. Okay, so this has no solution. There's no value for which you're going to take the sine of it, right, and get a 1.5. Over here, this one does. Sine x is equal to 1 at just one place on the regular circle at 90 degrees, right? You can think about that on the unit circle. You can also think about that on the graph, right? That place is right here. So the whole period is 2 pi. Right here is the middle. Sine is 0 at pi, and halfway between 0 and pi, or pi over 2, the sine function is 1. Okay. And of course, we should, say that this has a bunch of different, infinite number of solutions if we just rotate it 2 pi in. But we just wanted solutions. I didn't write it on the original problem, but they're just looking for solutions from 0 to 2 pi. So this is ends up being the only one, pi over 2. So I hope that helps show you how to do another one of these examples with the, trigonometric functions in equations. This was kind of cool because they hit a trig function in a quadratic.